So yeah, welcome everyone to this fall 2025 virtual meeting for the Black Hole Explorer. This is the first time we've ever done something like this, and we're so excited that you're all here to participate. So our goal is to bring together people working across the BEX project on science, engineering, mission design, and more. Uh, there's a chance for newcomers to get a sense of where things stand and maybe how they could participate or contribute, and a chance for those who are working on this day in and day out to hear new ideas and maybe change the direction that things are going or integrate things that we haven't thought of yet. So we're hoping that it's going to be really dynamic and interactive and really a lot of fun. For those who aren't familiar with it, the Black Hole Explorer is a project that's going to create a telescope 3 times the size of our planet, delivering the sharpest images in the history of astronomy. Um, and the driving goal and the most challenging requirements come from the objective to discover a black hole's photon ring. This is a very special feature that's expected to be in the images of all black holes that's made of light that has orbited the black hole before escaping. So it's danced right around the edge of the universe before only just escaping the gravity of the black hole. And when it reaches us, it has the imprint of the black hole's spacetime, allowing us to study black holes in an entirely new way. So in particular with BEX, what we want to do is make the first ever direct measurements of a supermassive black hole spin. But beyond that, BEX is going to be an opportunity to study dozens of additional black holes and their relativistic jets. And so these 3 thrusts form the core science areas of the BEX mission. This is being developed as a NASA Small Explorers mission. So this is a $170 million cost cap. And we are anticipating a proposal opportunity in 2026 or 2027 for launch in 2032. So we are at the formulation phase of the mission. This is the chance where new ideas can still be integrated. They can really shape the project goals and even affect the mission design at this stage. And so a lot is happening. If you'd like to learn more about where things stand right now, there's a mission overview paper that's part of a whole series of papers that were presented at SPIE last year. And you could look online on the website for things like mission fact sheets and so forth. Before we dive in, I want to give a huge shout out to the Science Organizing Committee for this meeting. So that's Andrew Shale, Peter Gallison, Mareki Honma, Sarah Isun, Alex Lupsaska, Daniel Palumbo, and Elliot Quadert. And in particular, Alex chaired this SOC and is also the project scientist of BEX. So big round of applause for Alex and the whole SOC for really creating an exciting program for us today. And so what you'll see today is a series of science talks across these core science themes, but then also things that push in new directions. So we're going to hear about prospects for studying binary black holes as well, connections to gravitational waves, possibilities of studying astrophysical transients with BEX, and even the kind of science that we can think about using BEX not as part of an interferometric array, but as a standalone single dish observatory. So there's a lot of additional science on the horizon that could either get integrated if we upscope BEX to a larger mission class, or if there's a follow-on mission in the future. So many exciting topics there, and huge thanks to SOC. As I said, the driving requirements for BEX are really shaped by this goal of detecting the black hole's photon ring. And that comes from the bending of light near a black hole. And most of the light is rather weakly lensed by the black hole, producing a diffuse image similar to what has been seen with the Event Horizon Telescope. This is light that's bent by a few tens of degrees. But it's a very special property of black hole spacetimes that photons can orbit the black hole before escaping, and that orbiting light piles up on this thin feature called the photon ring. So we think this is universal. It should appear in every black hole image if you're at high enough frequencies that the emission is becoming optically thin. And it's really strongly shaped by the gravity of the black hole. The reason that going to space is so important is because long baselines are imperative to isolate the signal of the photon ring. So on short baselines, the ones that we can access from the ground right now, the photon ring is blended with the signal from the diffuse emission and even the emission in the jet. Whereas if you go to those long baselines, all of that complexity fades away, and all you have is this damped periodic oscillation in the time average signal. And that is the telltale signature of the photon ring, where the periodicity here encodes the diameter of the photon ring along the direction of the baseline. So by going to these very long baselines, we can lock in on both the photon ring's size and its shape, and we can make direct measurements of whether or not these black holes are spinning, because the frame dragging of spin shapes the signal of the photon ring. Now, the BECS mission design has been a work that's grown out of years of effort, trying to pair the very demanding requirements of detecting the photon ring with the technology that we have today. So the final design is that BECS is a 3.4 meter antenna. That's basically the largest antenna that will fit within the fairing of something like a Falcon 9. It'll have simultaneous dual band observations at about 100 and 300 gigahertz. These two bands have complementary science. The lower band is particularly good at studying extended emission in jets, and the higher frequency band is better at peering all the way down near the black hole to study the photon ring, particularly to pierce through the strong interstellar scattering of Sagittarius star. And the reason we'd like to observe with these both simultaneously is both that is more efficient for observations, but also all of the phase errors are non-dispersive. And so we can use the more sensitive low frequency band to correct for phase errors in the high frequencies and to substantially improve the sensitivity of the high frequency observations. A major challenge for us is the data volumes that are required. So just like the Event Horizon Telescope, BECS will require petabytes of data to make these types of detections. And we're going to be downlinking the data at 100 gigabits per second using laser communications, this emerging technology that's really opening all sorts of exciting frontiers across astrophysics. BECS will have an orbital altitude of about 20,000 kilometers. That's long enough that we can get the angular resolution we need to detect the photon ring, but short enough that we still have the sensitivity to make those detections. And this will give us a nominal angular resolution of about 6 micro arc seconds when linked to the ground. And as I mentioned earlier, this is being designed for a 2032 launch. And these SMEX missions, the Small Explorers class missions, tend to be quite short. So it's being designed for a nominal 2-year mission. Throughout this virtual meeting, you're going to have lots of opportunities to hear more details about all of these different aspects. But I particularly encourage you to attend talks by Dan Moroney and Janice Houston, who are going to go into detail about the BECS instrument in tomorrow's morning session. If you'd like to learn more about the BECS spacecraft, Joe Shore and Ryan Pfeiffer are joining us from Lockheed Martin and can tell us about a lot of the development work that they've done that are making these types of spacecraft possible at this mission class. And Don Borison and Jade Wang from MIT Lincoln Labs are going to be joining us to give us a presentation on the evolution of optical communications and how that's led us to their readiness for the Black Hole Explorer. So that'll be in today's evening session. Now, with these mission parameters, what we've done is we put a lot of work into simulating what we would get for BECS. So here's one example. This is generated by Daniel Palumbo, who's the BECS simulations lead. And you can see these colored bands are the different 3 different BECS tunings, and the gray points are the ground baselines. So this provides the sensitivity required to detect a photon ring. And then we've also been putting a huge amount of work into understanding how we can then make inferences about the black hole spacetime. So this is just one example using fits to semi-analytic models, where you can see that once BECS is added to the mix, you can make very precise measurements of the black hole's mass, or more specifically, the mass to distance ratio. And this would also be the first ever measurements of the dimensionless spin of the black hole. And these are simulations of M87. So BECCS is at its heart a global project. We're going to be interfacing with existing radio telescopes all across the globe, most of which are already participating as part of the Event Horizon Telescope network. And in addition to that, we need optical ground link stations where we're going to be streaming these huge data volumes to Earth before they're all aggregated at a central correlation facility. So on the left is just showing the projected ground track of BECCS in its nominal orbit. And on the right, you can see what the interferometric coverage is. That's showing the coverage for M87. And so it fills in nicely and complements what we have on the ground. And the beautiful thing is that we actually get enough of our span here that it's fairly dense and filled interferometric coverage, which means that we can make images with BECCS. And this allows us to do all sorts of interesting things. In particular, by observing M87 every few nights over a few months, we can track not just images of M87, but dynamics of the source. The gravitational timescale is only 9 hours, which means that M87 evolves as we're watching it over just a few months. So this is one simulated reconstruction with BECCS. And in addition to studying the dynamics there, the time averaged image locks in on these sharp gravitational signatures that let us make the precise measurements of the black hole space-time. The other wonderful thing about images is it means that we're not constrained to just study special cases. We can look at lots of different sources across the sky. And it's kind of wonderful that some of the most interesting sources in the night sky studied at many wavelengths are bright in the submillimeter. So this is just an all-sky map showing some of the BECCS targets. Sagittarius Star and M87 are sort of our blockbuster targets. They're the ones where we'll be able to study the photon rings in our primary science targets. The red sources are an additional set of sources where we think we'll be able to resolve the mass to distance ratio and make images that are comparable in quality to what the Event Horizon Telescope already has. And all these stars, the blue sources, are additional active galactic nuclei that are bright in the submillimeter, and they're prime targets for BECCS. We're not going to study things on scales of the horizon, but it lets us connect those horizon scales to scales of tens to hundreds or even thousands of gravitational radii to understand how black holes interact with their environment. They drive outflows and even return energy to the universe. And these are not just random sources. They're really some extremely interesting ones. TXS 0506 is the first ever non-solar neutrino source. And so there's the opportunity to use the submillimeter observations at very high angular resolution to help understand what's driving the production of neutrinos in astrophysical jets, and maybe what the source of those emitting regions are. OJ287 is probably our best example of a potential binary supermassive black hole. It also happens to be very bright in the submillimeter. And the predicted closest approach of that binary system is something like 10 microarc seconds. So very well matched to the capabilities of BECCS. And then there's lots of other sources like this that have superluminal motion. They're bright in the gamma rays, and they really provide a very rich source of astrophysics to expand the BECCS science case and to understand the role of supermassive black holes in driving these incredible systems. The BECCS mission observing plan is being developed by Sarah Isoon. She's the science operations lead for BECCS. So this is just kind of a quick overview of it. What we're planning is that it'll be, again, a 2-year nominal mission. There would be 2 3-month observing seasons each year. One southern observing season that's kind of centered on Sagittarius Star, and the northern observing season that's centered on M87. So after the commissioning of the downlink and VLBI systems, we would rapidly enter this phase where we'll be observing lots of different targets and trying to fit them into a very dense observing program. And so if you have ideas about sources that you think are important to study with the Black Hole Explorer, this is really the moment that we want to start integrating those into the observing program. And I strongly encourage you to reach out to Sarah if you are interested in developing that. We live in a time of immense uncertainty, both nationally and internationally. But as the French author Victor Hugo put it, nothing else in the world is so powerful as an idea whose time has come. So even now, we've been able to make immense progress over the last year, and I think we're just hitting our stride and continuing to ramp up, even as there's quite a lot of uncertainty. So to give you a sense of where things stand, in January of this year, NASA released their SMEX announcement of opportunity. That same month, we were able to present BEX at the Winter AAS meeting. You can see Daniel Palumbo here at the mega booth, and many of the BEX interns. In April, NASA announced that the SMEX was postponed. So at that point, we were expecting a mission proposal in June. So we had already advanced through a series of what are called color reviews. We had a full proposal written, and we were really ready to go. But what we're doing is we're taking this extra nominally 1 year that NASA has given us to really push to accelerate the technology readiness of the instrument so that when we submit the mission proposal, it's even more competitive and compelling. In June of this year, we started the second year of our Black Hole Explorers internship program that's being led by Daniel Palumbo, and it's advertised on our website. We take interns internationally every year. And we've had five interns each year that the program has run, and that's funded through a gift from Mike and Amy Tudor. In June of this year, we also learned that the JAXA Space Science Committee officially approved the BEX Japan Working Group. So that's a big deal. This is a major international partnership for us that augments both our science capabilities, but also the engineering. JAXA has deep experience developing cryogenic systems that are exactly the specifications that are needed for the Black Hole Explorer. And so in the evening session today, you can hear more from Mareki Honma about all the activities that are going on in the BEX Japan Working Group. Earlier this month, we had a kickoff meeting, BEX en France. You can see a picture here. So that was held at the IRAM facilities, and are bringing together a lot of the scientists and engineers across France, which includes some of the key ground observatories for BEX also. And then finally, we just kicked off the next cycle of the Black Hole Initiative here at Harvard. And BEX is now one of the 4 pillars of that, and it's actually supporting some of the core engineering efforts of BEX. So right now, we're able to actually be pushing ahead every element of the BEX payload, doing technology development and testing and prototyping. So we'll have some really exciting results of that to show at the end of this fall. As of today, there's about 1 paper a week published on BEX Science, which is pretty good for a mission that's still in the pre-formulation phase. And it's already appeared in a number of different dissertations. So I think it's a really exciting time to be watching it grow through the efforts of these early career scientists, and we're so excited to be able to support all of their efforts. Okay, so what to expect in the next couple days? Each day, there are 2 3-hour blocks where we have a series of presentations. So we're starting off here. And after I wrap up this overview, we're going to have a series of 3 invited talks from Jenny Green, Andy Strominger, and Anna Ho, talking about different core science areas of BEX. We then have a series of contributed talks, and then we'll break until an evening session, at least in Eastern time in the US, where we'll pick things up with these updates from the BEX Japan group, then LaserCom, an out brief from a workshop last week at Wake Forest on spin measurements, and then some additional contributed talks. We also, at the end of the sessions today, will have an opportunity for sort of an Ask Me Anything format where you can raise any questions you have about BEX, science, politics, planning whatever you like, and we're hoping to just have a very open format there where we can get everyone on the same page. Then tomorrow we're going to have another series of really terrific talks. And after this first set of 4 science presentations, we have Dan Maroney and Janice Houston, who will be giving the overview of the BECS instrument, followed by the presentations from Lockheed Martin. Then in the second session tomorrow, we'll have 2 more invited talks by Ramesh Narayan and Charles Gammy on the black hole simulations that underlie the BECS science case, followed by additional contributed talks, and then a session where you'll get to hear some of the research projects from the Black Hole Explorers interns before we conclude. So really a lot here. We really hope you'll stick around and participate and ask questions to these wonderful speakers and think about new ideas for your own research. A few meeting guidelines. First, if you have a question, we hope you will, please raise your hand in Zoom and the moderator will call on you. As a courtesy to our presenters, please only use the Zoom chat for the current presentation. We expect that you'll have discussions that you want to continue, but do those in breakouts or on Slack or email, and just try not to use the Zoom chat for any side conversations. Please stay muted when you're not speaking. We'll be keeping an eye on that, and we'll try to keep things moving smoothly. And we encourage you to turn on your video. Let's get to know each other even in this virtual format, and especially when you're asking questions, it's great to be able to talk face to face. We are recording the presentations. If you're going to show any content that's not suitable for a semi-public release, please let us know, and we can make sure that nothing gets posted inadvertently. And if you have any technical issues, send a note to Paul Gardner. He has generously offered to help out with this meeting and has helped set up the Zoom. So a huge thanks to Paul as well for always keeping things running smoothly. So with that, I'd like to close. BECS is going to be the first sub-millimeter space Philip Guy observatory. It's going to take us to the edge of a black hole, and it's unlocking unique discovery opportunities. We know some of these. We don't know all of them. We want to hear your ideas, and we want to push the limits of what this is capable of. So thank you so much for participating this week and being part of making BECS possible.